hello everyone. Welcome to the WasmEdge community meeting. And yeah, let's get started. So we're gonna mostly do a recorded session this month, and so people can find what we discussed on the internet. Yeah, so we primarily have 3 talks for this for the next hour. I think that's our typical meeting lasts about an hour. So the first I want to introduce a demo and a use case of WasmEdge, and it's from Datasance POT, and so we have I see we have Emirhan Durmus here, and so I'll let him take over and discuss how to use WasmEdge. So please, thanks. Hello.
Thank you. Hi everyone. This is Emirhan. I'm going to share my screen. Let me share full screen. So I'm going to jump from the platform and the presentation. But before just jumping to the demo, let me prepare my screen here. Okay. Good. I think the presentation is visible, right?
Yes, I can see it. Thanks.
So thank you. Let's start. So again, this is Emirhan. I'm the founder of Datasance. We are a provider of a distributed edge computing platform, which is called POT. For a little bit background about myself, before I founded Datasance, I used to work for Fujitsu and SUSE respectively. I've been dealing with the edge and fog computing paradigm since from 2017, when the first Open Fog Consortium released its reference architecture for fog computing. Then right after I left SUSE, I would like to build a business with the idea of distributed edge computing. So edge is kind of a controversy when you are naming where the edge is. There are still some kind of community working groups on European Union to provide some kind of taxonomy for the edge computing or the edge devices. But edge is anywhere outside of our core network. There are lots of definitions on the edge side, like the service provider edge or user edge. But simply, as Datasance, we are focusing on the edge devices running outside of traditional data centers. These devices are either the source of data or they are the closest computer sourcing that we have, where the data is generated. So our main focus is these devices. In state-of-the-art paradigm, users need to deploy their services on these devices in order to provide autonomous use cases or something like that. The challenges from a user perspective, you need to handle all of this, software management stuff remotely, and there is a huge heterogeneity on the edge side. The operating systems might be different. The hardwares comes from different vendors, different CPU architectures, and of course, you don't only need to manage your services on the edge devices. Also, edge devices require some kind of peer-to-peer connectivity in order to create some kind of mutual intelligence on the operations side. These are the common challenges when we are talking about the distributed edge, especially in the outside of data centers. So what we are providing is an enterprise open source platform. We are one of the contributors of the Eclipse IOFOG project, and our platform is hardware agnostic. We can support both x86 and ARM architecture, And you may consider us as an extension of a Kubernetes environment. What we are trying to provide for our customers is kind of a building private clouds with geographically distributed edge devices. You know, our purpose is not just managing the softwares with the traditional containers. We would like to support WASM containers on the edge devices. And of course, we are supporting managing GPU workloads for edge services. And on the other hand, we are providing built-in distributed compute network for microservice to microservice connectivity and messaging. And our platform is integrated with Keycloak, so users can provide some kind of role-based access with it, and of course enable two-factor authentication, and if you like, they can integrate their Active Directory on top of it. So here's a quick architecture. As I said, we are positioning ourselves as a lightweight extension of Kubernetes. Our control plane is sort of Kubernetes native. We can deploy it on any Kubernetes that our customers have. We have, by the way, a CLI tool, which is called PostCTL. You may consider it as some kind of mix between the kubectl and Terraform. We are both managing whole customers can manage whole cluster with PostCTL, deploy their control plane, installing a new agent on the edge devices, or deploying new application, new microservices on these devices. Everything can be managed via PostCTL. And on the control plane side, we are deploying our control plane with our operator. Once PostCTL deploy a control plane on any Kubernetes environment, it deploys our operator and of course creates our CRD, and according to that, will services on the control plane side become available. And then PostCTL will install our agents to the edge devices. Our agent is the Java package, which is less than 30 megabytes, by the way. It's really lightweight. And once agent is installed on those devices and gets its provision from the control plane, and then all agents start to listen from controller which containers they are going to run. Their configuration, their environment variables, and of course the routes regarding to microservice messaging. By the way, our built-in message bus uses Scupper routers. You may know Scupper from Red Hat folks. It's the fork version of Apache Qpid dispatch router, by the way. And once everything is set up, users can, let me move to demo environment. Here it's the dashboard that users can manage their clusters also. There's one example over there. I have one agent. Let me show also here. Oops. As you can see, when we deploy our microservice via our CLI or on the dashboard side, the agent listen which container this device is going to run, and just talk with the container engine APIs and start services. While deploying services, by the way, users can choose which container runtime they would like to run this microservice. Actually, this is the point where we are interacting with the WasmEdge community. We have built-in, while PostCTL installing agent scripts, it also checks if there is Docker installed, and then if it installs WasmEdge container dshims on those devices. So we are once the agent installation is complete, it's ready to run both traditional and WasmEdge containers. So users can just define which runtime they would like to use and its platform, and of course, if there's a GPUs that they would like to attach to container runtime, they are just choosing over there and just pushing the application via YAML. Let me show another example here. I have another agent, another device. Actually, it's empty device right now. I'm going to install it and I just need to run here right now. This agent is new agent comes. It's deploying right now. And while it's deployed, let's create a new application template for the Wasm app. Let's say it's going to be run part. Okay, it's ready. Let's check it. So while it's deploying, I'm going to explain a little bit about our internal message bus and how users can use it. Agent is just not running the containers that it gets from the control plane. It also provides local API for microservices, which is for the configuration parameters and also for the message bus. And the developers don't need to think about the network underlying whole edge devices. We are providing layer 7 distributed mesh network. So in the case that microservice is using our SDKs and talk with the agent local API, it just need to publish a message or subscribe the message. It's really easy for developers to create services that can send the message each other. And just while deploying the application, you are going to choose on the root of the deployment YAML that which microservice is going to be subscriber and which one is going to be publisher. And then the whole routing configuration is done automatically via agents running those microservices. So they can start to send messages each other. And there is another also feature, what we are call is public port proxy. By the way, our new agent is up and running right now. Let's deploy our new Wasm application on it. Let's say that. Yep. Now we pushed our application. Right now, new microservice is starting on the new agent. Let me refresh my screen. So it's up and running, and let's check from there also. Here, as you can see, the WasmEdge also running right now. And what we have, by the way, is called public proxy. You know, those edge devices are sometimes running as like accessible by publicly. So you don't need to expose their IP address or something like that, but you would like to expose the service endpoints running on those edge devices to your backend or to your publicly. So what you can do is just define public port proxy enabled for these microservices, and it creates automatic proxy between the edge node and the control plane, and you can access your microservice endpoint over a secure, IP. It's a really cool feature if you would like to expose any endpoint to publicly or to your backend services. So let's just deploy another application, which is a traditional containers. This time it's not going to be, WASM containers. So as I told, we are supporting both traditional and WASM containers because we believe that customers need both of them in their use case. So we are supporting each one of them, and this will be an application that has two microservices, and again, one will be publisher and one will be subscriber. So one is going to run on the first agent that we looked before, and the other one is going to run on the newly deployed agent. Yeah, it's deployed right now. We can see its status and everything like that. You know, by the way, I forgot to mention something about the dashboard, but on the dashboard side, you can, see health status of your agent, its resource consumption, and of course, you can manage your, services status, and you can easily configure your agent, by the way, if you would like to, make some configurations regarding the agent configuration. So last feature I'm going to mention, I think, which is quite helpful for our users and customers, which is called application template. While if you have an application and you would like to spread it on different nodes with a different configuration and variables, you can define, let's see, okay. You can define some variables for your application templates. And here is an example from one of our partners product. It's an industrial IoT microservices running on the edge nodes. It uses, by the way, the NUTS messaging system. And I'm going to mention a little bit later, we are also providing a NUTS server as our catalog microservice. And once you create your application template, it's going to be really easy for you to spread it all over cluster. Just while deploying your application, you are choosing which template you are going to run, and just define your variables, and then everything is going to set it up on the agent side. So the last thing that I'm going to mention regarding the NUTS, and with this way, I am going to also explain how agents local configuration endpoint works actually. Here is our NUTS service. Users can easily create NUTS leaf nodes or NUTS server deployment on our edge nodes. While creating, the YAML, users can just define arbitrary key value parameters for microservice configuration. And once microservice get this configuration from agent local API, it just create its NUTS configuration automatically, and users don't need to, add some kind of NUTS configuration files on the Edge side, or well, if they would like to, add some kind of certification with the NUTS, they don't need to push their TLS certificates as a file on the Edge nodes. They are just defining them on the config side, and everything is going to be running inside the container. So these are the things that I have today, actually. Again, to make it summarize, we are a kind of a platform. We are a lightweight Kubernetes extension, and we are supporting both traditional containers and WASM containers. We are not providing some kind of hosted solution, by the way. Everything is running on the customer side. We are totally Kubernetes native and positioning ourselves as an extension of Kubernetes environment, and let users to deploy both traditional and WASM containers on any edge devices that running outside of traditional data centers. Thank you. So if you have any question.
Oh, yeah. Thank you, Emirhan. That's really impressive. That's the first time I've seen this in detail, although I heard of you guys, but that's I'm really quite impressed. So so this is based on Red Hat OpenShift. So you are using CRIO and the CRUN as your runtime. Is that correct?
No, on the edge side, actually. By the way, everything, we are managing containers outside of, the edge devices outside of data centers, like
Okay.
a bus PC or some kind of edge gateways on the, utility grids. And on the container sheet, we are using Docker as a container engine, by the way. We are not using Podman right now. We are using Docker because, most of the operating systems are on those edge devices are based on Debian or Ubuntu. So right now we are preferring to move with Docker and containerd. And the containerd folks working on Runwasi, they would like to provide containerd schemes for both WasmEdge, WasmR, and WasmTime. We are packaging these binaries as a Debian and RPM package. So once PodCTL installs our agents, also containerd WASM schemes are installing from our repository. So users don't need to do any manual installation. So actually right now our architecture is based on containerd schemes.
Okay. That's very cool. Yeah, that's because you have OpenShift here. So sorry, I assumed that's
yeah. For OpenShift side, this is our control plane. Our control plane runs on any Kubernetes. So it's also certified on Red Hat OpenShift marketplace, by the way. Our operator is certified for both OpenShift marketplace and also Kubernetes community operator hub. So that's why the OpenShift logo is there.
Cool. Yeah, then we really need to get our the GPUs working in RunWasi so that we can run those lightweight AI application on the edge, which is really popular these days. So yeah, that's something that's fairly high priority on our end. Is to get that.
That's why actually, while making this WASM integration, WASM support with our platform, we also add CDI devices support for the microservice side. So while I also believe that with the WASM and the GPU, everything will be much more easier on the edge side for AI.
Yeah.
So that's adding both CDI device support and WASM together right now.
Yeah, because that allows you to run like Apple Intelligence, right? Some those smaller models on the device. That's it's because we've seen a lot of use cases where people want to run like vision models or OCR models on their camera, things like that, and then have the bigger heavyweight models running on the server. That's like you said, as a microservice, right? But something on the device, smaller models on the device, larger models on the server. But that's great. That's that's I really appreciate that. You coming to talk about this. Oh, by the way, so is the project part of the Eclipse Foundation? Because I also see Eclipse.
Yep. Our code base is the fork version of Eclipse.io fork. We are, Eclipse.io fork community is there are not much things happen on the community right now. Since we say, hey, we are here, we done lots of improvements. Right now, we are merging our code base to Eclipse.io fork project. So a new release of the new community release of the IO fork is going to be use our code base. We done lots of improvement on the IO fork side. So we are open source. We are always going to be open. It is the first thing that we are mentioning while explaining our company, by the way. We love the open source culture and we are always going to be there. So everything I explain regarding our platform is going to be, merged with the Eclipse.io fork. So.
Oh, excellent. Yeah, that's we definitely should do more with our BTM2 communities. Yeah, that's thank you. That's I learned a lot, and it's I definitely will try it out. Yeah. So, but by the way, if anyone have questions, you can ask in the chat, or you can just that's because I think we have more casual format this for this month. So yeah. Okay. Yeah. So let's move on to our next topic. Our next topic is application called TalkTalk. That's it's one of those applications we demoed at KubeCon at Salt Lake City, and which people seem to love it. And so we invited the author of this application, Sam Liu. It's to talk about that. And give us a demo in our community meeting. It is one of the I think more interesting AI applications that I saw. Where you can do I wouldn't say real time, but close to real time chat with your large language model everything running on your own device. So Sam, are you ready?
Yeah.
Okay. All right. So I'll pass mic to Sam. Okay.
Wait a moment. Okay. Can you see my screen?
Yes.
Okay. Let's get started. Okay. I will give a introduction to TalkTalk, a voice-to-voice AI app using LlamaEdge. Okay. TalkTalk is a lightweight voice-to-voice AI app, and it supports multiple languages, such as English, Chinese, and Japanese, and etc. The front-end part of TalkTalk is created with Gradle and also use some Python code. And the backend part is powered by LlamaEdge. We use two types of API server. One is Whisper API server, which is responsible for converting audio parts into text. And the second one is Llama API server, which is responsible for chat completion tasks. And later, I will show you a demonstration. In this demonstration, for the purpose of demonstration, we also introduce a third-party library named GTTS, which is responsible for converting text to audio. We use the purpose of using GTTS is to demonstrate that LlamaEdge API servers can work with third-party services or libraries. And okay, TalkTalk project, you can find it in GitHub here. Okay, this diagram shows the major components. On the left side is the part we want to introduce is LlamaEdge servers. Llama proxy server is responsible for forwarding user requests to the downstream API servers. For example, here, Llama API server and also Whisper API server. And on the left, on the right side is the TTS part. As I mentioned in the previous slide, we use GTTS here. In this diagrams shows the workflow of TalkTalk. Users send their questions, of course, via microphones, and TalkTalk will send the user questions to Llama proxy server, and the proxy server will forward the user question, of course, in wave format to Whisper API server, and Whisper API server will transcribe the voice and into text, then return the result. In the second stage, TalkTalk will send the transcribed text question to Llama API server, and the Llama API server will generate the final answers based on the questions user asked, and then return the answers back to TalkTalk. Of course, we are proxy server, and in the third stage, TalkTalk will send generated text to here is Google GTTS library, and Google GTTS will be responsible for converting the text back to the voice, and then return to TalkTalk. And finally, TalkTalk will show the final voice answer to users, and user can play back the voice, of course. Okay, because the demonstration will use microphones, and the Zoom also use a microphone. So to avoid the device conflicts, I just prepared a demonstration video in advance. So I don't just demonstrate the details and just play back the video. So wait a moment. Okay. video, I will demonstrate a voice-to-voice AI app named TalkTalk. Now, let's get started. First, let's start LlamaEdge proxy server and two API servers, which are the backend of TalkTalk. Llama proxy server is responsible for forwarding user requests to the downstream API servers. And Llama API server is responsible for check completion tasks. And Whisper API server is responsible for audio transcription tasks. Okay, after starting the servers, let's register downstream API servers into proxy server. First, let's register Llama API server. Next is Whisper API server. Okay. Okay, now the backend part is ready. So let's start TalkTalk. Okay, TalkTalk is running. Okay, now let's ask two English questions. What's the capital of France?
Paris.
Okay, we can also see the user's question on the left side, and on the right side is the answer generated by the model. Okay, the answer is correct. So now let's ask one more question, a more complex question in English. How many planets are in the solar system? Please list their names. It will take, okay. Okay, great.
There are 8 planets in our solar system. Here's the list: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune.
Okay, now let's ask two more questions in another English language used in Chinese. Okay, the first question I will ask is in which city in China is the Terracotta Army of Emperor Qin Shi Huang located? 秦始皇兵马俑位于中国的哪个城市？
秦始皇兵马俑位于陕西省西安市。
Okay, the answer is the location is Xi'an City of Shanxi province. Okay, let's ask one more question in Chinese. The second question I will ask is in which city in China is the Great Wall located? 长城位于中国的哪个城市？
长城位于中国北京。
Okay, the answer is correct. Changcheng is located in Beijing of China. So that's all. Thank you.
All right, thank you, Sam. Yeah, that's you know, so I thought the multilingual part was very interesting because the AI would be able to identify, that's whatever the language you speak, it would be able to identify that, and then the large language model would be able to respond in the language you are giving it, right? So that I thought that was a very interesting use case. So the other thing I want to really emphasize is that when Sam runs this demo, we run this demo, everything actually runs on a single computer. That's voice recognition, the large language model, and everything is running on in our case, a single MacBook. A fairly old one, the 3-year-old MacBook as well. So you can see if you have a faster GPU, you can really make it nearly real time. So meaning that you can have sort of like a telephone call experience, right? You can respond immediately after you stop speaking. And so the other thing I want to mention really is that, so Sam, correct me if I'm wrong, is that currently we are using the Python package for voice synthesis, so turns a large language model text into voice. But we on LlamaEdge, we actually have an experimental project called TTS API server. So it is provide open AI compatible TTS server. So so basically give it text and choose a voice. It's gonna synthesize a voice file for you, right? I think in the near future that we want to switch to our own stack. So then all 3 components would be running on WasmEdge. And they can all run on the smaller edge devices, right? From voice recognition to voice-to-voice large language model, text-to-text large language model chat, and then text-to-voice TTS, right? So that's I really look forward, to demonstrate the whole thing on WasmEdge. So yeah, that's what I find particularly interesting is that at KubeCon, even on the conference show floor, even if that's very noisy, and this by having everything running on your own computer, you can move it around. You are not affected by the Wi-Fi, and delivers a pretty good experience. That's yeah. Thank you, Sam. So that's let's keep improving that, and let's see find more use cases for that. Thank you. So okay. Yeah, so let's go to our last topic of the day, and which is what I thought was very interesting because I don't know if you guys know about the Flatcar Linux. Flatcar Linux was a Linux operating system that's specifically built for containers. There are 2 meanings for that. One is that it's an immutable Linux operating system, and Hydai will explain what that is. That is very good at so all the applications on the operating system is in a container. So it's really good at running container applications. And on the other hand, because it's immutable, so the operating system itself is built layer by layer like a container, right? So it's so it is both a really good container host and also a really good container-like. As a way the operating system is built, it's also really like a container. So Flatcar has recently been donated by, I believe, Microsoft to the CNCF as a sandbox project. And when we met them at KubeCon, they were positioning themselves not only as a container operating system, but also as a WASM operating system. So basically, on their booth, they have a slogan to say, WasmEdge, and so the first time I saw that, I thought it was WasmEdge, right? So I think it ties into a lot of the topics that we discussed today with maybe with Emirhan. You know, that's so to have the workload be deployed onto edge devices in a lightweight operating system package. You know, so I know we already have a solution that's runs WASM directly without the operating system, or you just using the host. But in some scenarios, you know, that's people want to have the to have some minimum operating systems that provide isolation. So after we talked with the Microsoft folks at KubeCon, we decided to integrate WasmEdge and also LlamaEdge into Flatcar so that they become what they call a layer on Flatcar, so that when you build a Flatcar image, you can have the WasmEdge runtime or the LlamaEdge runtime being built into it. So that's the work that's Hydai have done. You know, that's, I believe, both PRs has been merged, in the Flatcar repo. So, I'll let Hydai talk about that. Thank you.
Okay, let me share my screen.
All right.
Can you guys see my screen now?
Yes.
Okay, great. So today I'm going to talk about how to back in WasmEdge system extension image for the Flatcar Linux. So basically the systemd system extension image is overlay image for the slash user. So it will allow you to deploy any extensions, including some binary, some software, or any library you want, and to extend your best operating system image with it. So since the Flatcar container Linux, it doesn't allow you to use the package manager. So it's not a good idea to, because it's an immutable operating system, so it's a good idea to use these extensions via the system extension way. So let me talk about this repository. This repository is called the System Extension Bakery, and basically it provides a tool to create the images, including you can create lots of different extensions, including the Llama, the WasmTime, WasmEdge, LlamaEdge, and lots of, you can check this repository and you can find out there are lots of different extensions that you can build by yourself and just mount them to your Flatcar container Linux to extend your features. So if you want to, build this system extension image, here are some dependencies that you should install on your system, and then you can check which software you want to build. For example, if you want to build the WasmEdge, you will find out there is a script called create WasmEdge system extension, and execute it. You will create the WasmEdge.raw file. And basically, all of the software you need is bundled in this layer. And we already have two pull requests merged into this repository. So if you want to build WasmEdge or the LlamaEdge, you can just use these two scripts to build the images and just deploy it to your clusters. Yeah. So here is the process you will show when you call this script. And for example, if you want to create the WasmEdge, you will need to specify which version you want and the output name you want. So if you execute this script, you will download the WasmEdge 14.1 and unzip all of these files. And then you will create the Scratch file system and just zip all of these files into the WasmEdge.raw file. and then you will get this one. Okay, once you have this one, then you have to write your configuration to deploy it at the very beginning of the initialization stage of your Flatcar Linux. So you will have to write configuration to specify which system extension you want to use. So for example, this one is how we deploy the WasmEdge and with the Flatcar operating system. So you will specify your storage. For example, here is the path of the WasmEdge raw file, and then you will specify the source. For example, you will download from anywhere, and then you will try to link it to from the extension folder to another folder. Okay, and when you set up of this one, actually it can be updated by just overwrite this path. For example, this one. So if you want to upgrade your extensions, the only thing this system extension service need to do is to download a new version of the WasmEdge, the raw file, and then use the link to overwrite the original one that the upgrade is done. So it will be very helpful for you to deploy the service, to upgrade the service. Yeah, so this is a very basic configuration you can use. And once you have multiple different layers, you can add more like more passes, more links to set up your whole environment. And then before passing this configuration to the deployment, you will need to transpile the YAML file to the JSON file. And basically, there is a tool to do this for you. So you just need to use the tool from CoreOS to convert your YAML to your JSON. And after you get a JSON, and you can deploy your container or your virtual machine with this configuration. So I am using the DigitalOcean as the example. So basically, when you get your API token and you have your Flatcar container image, and you have set up your SSH key, and of course your configuration. Once you prepare this for information, you can ask to create a new instance with this configuration. Okay, so once you deploy it, you will create a new instance, and then here's the output. If you deploy the whole things and you log in, you're going to find that, oh yeah, we are already on the Flatcar container Linux, and this is deployed on the DigitalOcean, and you can just execute any software you installed. For example, if you are using the WasmEdge system extension, you can just call the WasmEdge to execute any Wasm file. For example, we execute a very simple Wasm file to add 1 and 3. Yeah. And if you extend more, for example, if you add the LlamaEdge API server, and you can check this link. Sorry, you can check this link. I have an example to start the Llama API server, so you can interact it with just like you interact with the OpenAI compatible API server. So yeah, this is the whole story. That's how you create your own system extension image, how you use it to write the configuration file, and then deploy all of it to your instance and use it. Yeah, so that's all of my session. Yep.
All right. Thank you so much, Hydai. So this also supports GPUs, right? That's
Not yet.
Okay.
These pull requests only support the pure CPU, and I have not yet verified the GPU parts. So after all of the thing is verified, then there will be a new pull request for it. Yeah.
Got it. Yeah. So because you said one of the steps is to create your own CSS extension and then get the .raw file. Can I use the .raw file you already built? So that I
sure.
don't have to mail. Yeah.
Sure. Yeah.
So I just choose the right platform and
yeah, you just choose the right platform. Actually, just change this link to any pre-built raw file. Yeah.
Okay. So yeah, that's so I think that may be easier for people, right? Because because then you can also skip the step of converting YAML to JSON. You can just have one JSON, right? That's yeah. So that's maybe easier. That's so yeah, that's a lot of people have asked, why do you guys need to do that? So because we have seen Emirhan had demonstrated we can use Kubernetes to orchestrate the WASM container directly. That's but the WASM container has to run on some kind of a host system, right? Some people depending on your comfort level, some people on the edge devices it might be the right way to do it, but some people also run other features in the operating system that may or may not be provided by the host, right? So they want a more containerized environment. So we also see a lot of people to run WASM inside the container. That's they build their own container and they put WASM in there. And then run it like that, right? But that's but on that end of the spectrum, it's too many variations. It's really difficult to lock down anything. Because the container can really be anything. You can have any operating system. So I think the Flatcar Linux really provide a way for security and for efficiency minded people to deliver essentially still a Docker image has a guest operating system which isolates itself from the host, but with a very tightly controlled set of things. So I really look forward to see LlamaEdge running on GPU because that would really allow us to replace those 5 gigabytes PyTorch container that people use to run their AI models, right? So with this we can have a very locked down and very the container would just have the dependency, which is device driver and libc and LlamaEdge, and then have it run what we call cross-platform workload, meaning that's the application itself does not need to be aware of the GPU underneath it, but but the container would contain the right driver, right? So the application developer would only need to compile it once. He doesn't need to know which version of the GPU driver he's running on. So yeah, that's we're very excited to see what's going on. To see future opportunities with Flatcar, especially now they are also a CNCF project, and I believe you can also do this on Microsoft Azure, right? Although you demonstrated DigitalOcean, but I think Microsoft Azure would work just fine, right? Okay. Well, thank you, Hydai, and I think we are up at for the hour. So if you have questions for any of us, feel free to to raise them in the chat. But if not, that's we can take this discussion offline. And if you have any comments, questions, please do come to our GitHub repository, and or find me on on my email, michael@secondslate.io. Just we can take this discussion and and talk about that more offline. So if there's no other questions in the chat, I think okay, all right. So let's conclude this community meeting. Thank you so much, everybody, and we'll see you next month. Bye bye.